Hello everyone, I'm Chun Young-ho from University of Seoul in Korea. In this talk, I'm going to present our work to achieve a real-time CNN inference on a mobile GPU. The need for on-device inference is ever increasing for various reasons such as privacy issue. However, it is very challenging to achieve real-time inference of CNNs on mobile GPUs due to limited computing power. A mobile GPU has much lesser number of computing units, or SMs, than that of a server GPU. The inference of CNN for a single image usually takes a few milliseconds on a server GPU, but the same network takes more than 10 times of inference time on a mobile GPU. Sometimes it leads to hundreds of milliseconds. In this work, we focus on the recent trend in CNN that the number of layers is increasing while the workload of each layer decreases. Many CNNs usually have hundreds of layers. This trend introduces a new performance bottleneck called kernel launcher overhead. The kernel launcher overhead is actually a well-known overhead. Each layer in a CNN is usually implemented as a GPU kernel, and the kernels for the network are launched one by one from the host. Each time a host in the CPU launches the GPU kernel, it takes a small amount of time for the invocation, which is known as kernel launcher overhead and considered to be negligible. On server GPUs, it usually takes only dozens of microseconds, accounting for less than 1% of the execution for the most GPU kernels. However, we found that the kernel launcher overhead is significant on mobile GPUs. For example, in Retina Face, a recent CNN of our interest, the overhead leads to even 24%. Among this 24% of overhead, the well-known host-side overhead only accounts for 6% point, and the other 18% point accounts for the device-side overhead, such as work item creation. We call the kernel launcher overhead, including this device-side overhead, effective kernel launcher overhead. To reduce the effective kernel launcher overhead, we propose to adopt person thread-based GPU execution model. Person thread is launched only once and iterates over a loop until all the job is completed. It is often implemented as a back kernel where all the computation is merged into a single logic kernel. Obviously, there is only one kernel launch. Note that the person thread-based executions were originally proposed to fully utilize the massive number of computing units in a server GPU. Thus, they require worker queues, which we eliminated for the efficient execution. The contribution in this work is that we mainly tackle a new problem of effective kernel launcher overhead to achieve real-time CNN inference on a mobile GPU. Our solution is to first adopt person thread-based execution. We also exploit into a quantized convolution on mobile GPU, as well as providing automatic conversion from FP32 to into 8. Finally, our online profiler finds the best option among different choices for the convolution, such as quantized or not quantized convolution. In the following slides, we will see the components in detail. To minimize effective kernel launch overhead, we adopt person threads. It is basically a Mac kernel approach where all the layers are implemented in a single kernel. In contrast to the original Mac kernel, where kernels or layers are executed concurrently, a CNN is executed layer by layer in our inference engine, not using any dynamic scheduling in task queues. That's because they use cost only overhead without any gain on a mobile GPU, as the number of computing units is small. For each layer, a work group computes an output channel of the output picture map and iterates to process the entire channels. As convolution layers need some reduction among input channel of the tensor, global barrier synchronization among work groups is required. The global barrier synchronization is realized with a counter, which is incremented atomically as the processing of each output channel is completed. If the value of the counter reaches the number of channels, the work groups can move on to the next layer. Note that all work groups in a Mac kernel must be active in order to avoid any deadlock. To achieve real-time inference, making use of quantized convolution is essential. However, the existing frameworks such as TensorFlow Lite do not support integrated convolution on mobile GPUs yet. Also, ARM Compute Library, or ACL, does not support quantized convolution if a network includes batch normalization layers. In this work, we provide full support for into-8 quantized convolution on mobile GPUs. First, our framework includes an automatic into-8 quantization tool that converts FP32 data into into-8. Once the user provides a pre-trained model and calibration dataset, our into-8 quantization preparator converts the data using KLD and folds fetch normalization layers into convolution layers. On the other hand, more and more recent mobile GPUs have integrated special hardwares for neural network acceleration. We also exploit one of those hardware for into-8 dot product. Then, we propose some optimizations for the into-8 convolution, such as not using into-8 convolution for the leaf layers of CNNs for object detection, because we observed it could result in significant accuracy loss. To prevent redundant quantization, the quantization is implemented as a separate layer in our person thread-based execution, rather than it is implemented inside the convolution layer. In our observation, the into-8 convolution does not always lead to better efficiency. Occasionally, the overhead for quantization and dequantization is larger than the benefit of the quantized convolution. Similarly, direct convolution is sometimes faster than the matrix multiplication-based one, because of the loading overhead. As no single method can outperform the other methods, we propose an adaptive execution through online profiling. The inference engine tries each configuration for first few frames and then selects the best configuration. The later frames are processed with the best configurations. In our current work, there are 4 possible combinations for convolution layer. That means 4 frames are required for profiling. We evaluate the proposed techniques with a commodity mobile device, Samsung Galaxy Note 10 Plus. It equips with ARM Mali G76 and P12 GPU, where an into-8 dot product hardware is integrated. With the special hardware, into-8 dot product operations with 4 elements can be computed in a single cycle. The baseline in our experiment is ARM Compute Library, or ACL. ACL can be thought of as a low-level library for deep learning, like cuDNN for NVIDIA GPUs. We support CNN Inference in the form of ACL graph. We use ACL graph for comparison. In the evaluation, we use Retina Face, a state-of-the-art face detector and localizer. It uses MobileNet v1 as a backbone network, which means the workload per layer is small and the effective kernel launch overhead is large. The number of kernel launches in the ACL implementation is 144. As a result, we achieved a super real-time inference of Retina Face. The latency of 22.96 milliseconds corresponds to 43.5 frames per second, which is 2.01 times our speed up over the ACL implementation. The best configuration is obtained by the online profiler from the 4 possible combinations. In this configuration, all of the possible choices are employed. The accuracy for Retina Face was measured using wider face dataset, and there is a little accuracy drop of 0.31 percentage point in the proposed approach, even if it exploits into-8 quantized convolution. We also evaluated the benefit of the hardware into-8 dot product in Mali G76 GPU. It was confirmed that the hardware can reduce the execution time of convolution layers in Retina Face by 1.24 times on average. In summary, we first identified an important overhead in on-device CNN inference on mobile GPU, which is effective kernel launch overhead. To achieve real-time CNN inference on a mobile GPU, we proposed an inference engine where person thread-based execution model is adopted to avoid significant kernel launch overhead, and into-8 quantized convolution is exploited with special hardware support, and online profiling is used to find out the best configuration. As a result, we could achieve 22.96 milliseconds of latency, or 43.5 frames per second, for Retina Face on Mali G76 GPU. With that, I'd happy to take any questions. Thank you.